I would first like to thank Heidi Fern for inviting me to this workshop, and I would like to acknowledge Jim Woodward for many useful discussions, and of course my UC Merced collaborators. Professor Jay Sharping was supposed to speak after me today, but unfortunately his son had to have surgery, so suddenly he couldn't make it. Luis Martinez was my student and now a postdoc at Livermore, and we hope to collaborate on some of the, well, I won't talk about the experiments that will be hopefully started at Livermore in collaboration with George Kaplan, whom I should list here, but I didn't. He's a theorist at Livermore who asked some really crucial questions like, is there a Casimir effect for superfluid helium? And I think the answer is yes, and I'll talk about it today. There's also...
What was Jerry Kaplan?
It's George Kaplan.
Yeah, he's been there for a long time.
Oh, yes, right.
Yeah,
And
I remember.
he has also been ostracized by the mainstream GR community. And, well, I won't get into that. What?
I'm not surprised.
Well, I'm also in that ostracized community too. Bangsu Kang is my postdoc. He's very unusual. He was a judge, in South Korea. He was a major judge, maybe in the Supreme Court or its analog there. But guess what? He decided after retirement to come and work with me as a graduate student. It's amazing. And so he's now a postdoc of mine. Nathan Enon is a graduate student who some of you may have met. I think Jim knows him, and Heidi, you met him. And he has been working on theory in general relativity, especially on superconductors and how they interact with gravitational waves. And I won't get to speak about that today. I have I'm sharing a really excellent student with Jay Sharping named Jake Pate, and he has invented a conical tip type of actuator, which I'll tell you a little bit about, which is, I think, going to be very important in future work on propellantless propulsion. Tell you about that. I hope he doesn't mind, because this is really his idea and he hasn't published it yet. And then present here is Jonathan Thompson. Will you stand up, please, so everybody can see you? This is Jonathan Thompson. His initials said it all, J.J. Thompson. What a name. And he'll give the next talk on behalf of Professor Sharping, but he'll also talk about his own work with Gerardo Munoz at Fresno State on Reisner-Nordstrom, or charged black holes, which is purely general relativity, but he is also amazingly excellent experimentalist. So if you're looking for a good combination of theory and experiment, here's the guy to hire. Okay, so he'll talk after me. And then, let's see, is anybody else that I forgot? Oh, I would also like to thank, but he's, of course, no, it's a long time ago, but Peter Maloney, who first introduced me actually to the whole idea of propulsion in a workshop at Cleveland organized by Mark Millis back in the 90s, at which conference I met for the first time Jim Woodward, I found out, and Robert Forward, who unfortunately passed away. But at the time, I thought that frankly, this was an, crackpot But because of Peter, I attended just out of curiosity. But it's really interesting how interestingly that things have turned out now among the crackpots at this conference. Okay, so I hope to convince you that it's not a crackpot, it's mainstream physics that I'm going to introduce you to. We'll see. Yeah. Please feel free to ask questions as I talk, okay? Okay, so let me start with why study Casimir effects, okay? I'll tell you what the Casimir effect is in a nutshell. If you have two conducting plates and both of them are charge-free, they are grounded, so there are no charges. Nevertheless, they attract each other. And this is the Casimir effect in a nutshell. Usually, people think of this as vacuum fluctuations pushing the plates together from the outside. But I am going to present to you an alternative point of view, which is that correlated currents between the plates is what's doing it. Okay? And that's my point of view. But in any case, it's quantum fluctuations that give rise to the Casimir effect. Now, the physical vacuum, and I stress the physical vacuum, this is, the vacuum emptied of all matter. That physical vacuum is, of course, a unique physical reality. We know that physics deals with this unique reality called the physical vacuum. But we can describe the physical vacuum from two entirely different points of view. And the first one is, of course, from general relativity. General relativity teaches us, Einstein taught us, that we should think of the physical vacuum as, let me get this, as a non-fluctuating, and I stress non-fluctuating space-time. Put it in different words, space-time is a classical continuum, a manifold which has no fluctuations in it whatsoever, okay? That's the picture introduced to us by Einstein in general relativity. However, on the other hand, in quantum mechanics, the physical vacuum, for example, the quantum electrodynamic vacuum is fluctuating all the time. It's a fluctuating vacuum in which particles and antiparticles appear and disappear all the time due to the uncertainty principle. So this is, in fact, not a matter of trying to reconcile. I think this is irreconcilable difference between the two theories of general relativity and quantum mechanics. But this suggests that the way to attack this problem is experimentally. We should look for experiments, what Newton called experimentum crucis, which in Latin means a crucial experiment that should decide which theory is right. Okay? Yes.
But there is the point of view, for example, Professor Susskind at Stanford, that the general relativity mathematically admits as a solution gravitational waves with infinitesimal perturbation that are spontaneous without any source. You can have just as a solution, mathematical solution of general relativity equation, that is a solution. And those are fluctuations.
Yes, but I don't understand string theory, and that's where he's coming from. And I don't see how you still can reconcile Einstein's space-time, which treats space-time as classical, non-fluctuating, with that picture. I like to see the details of how you could get a fluctuating space-time out of string theory. Okay?
Not string theory, just general relativity. In his course, Susskind's course on general relativity, he discusses this. It's just mathematically, it seems equation is a nonlinear differential equation, admits this as a solution.
Oh, I'm not familiar with this kind of solution. I'll have to look at it, okay?
Yeah, you say that there's no fluctuations in space-time, but general relativity does. Einstein put in a cosmological constant, which gives energy to the empty vacuum. So what is
Right.
it that's containing that energy if it's not fluctuating?
Well, but if you look at the Einstein equations with the cosmological constant, it's still a classical field theory with no fluctuations in it. Yeah, I mean, formally. I mean, just mathematically speaking, it's differential equations with no fluctuations.
Yeah, but it's a number which represents something that contains
Oh,
energy.
yeah, but that's something added to the Einstein theory.
Yeah, I understand. He added it to keep the universe from falling.
Right, exactly. But the extra step to say the cosmological constant is due to vacuum fluctuations is not in Einstein's original theory. Einstein's original theory is a classical field theory. End of story. No fluctuations. Yes.
I thought they were talking about the fluctuations in gravitational fields, so you can build up a bigger field from gravitational waves and build up a black hole from gravitational waves. I thought that's what they were about.
Who's they?
They being gravitational wave people, they would say that you can build up a black hole from gravity waves, and small fluctuations can make bigger fluctuations in experiment. I thought that's the fluctuations.
No, I don't agree with that. Okay, here's my understanding, and I may be wrong, that well, okay, I'm presenting is in a paper I read about by Wald. Wald says you can embed curved space-time. I'm sorry, you can embed quantum field theory into curved space-time, but the curved space-time is treated classically. It's just like in our field of nonlinear optics or quantum optics, where we treat the electromagnetic field completely classically and the matter quantum mechanically. It's a semi-classical theory, right? That is the nature of things, and I don't think people have a quantum theory of gravity, which is required if you want to actually have quantum gravity, and that doesn't exist as far as I know, unless Susskind has solved the problem. Maybe he did. I just don't know. I doubt it. I have to tell you a little joke. My thesis advisor at Princeton, you know this, was John Wheeler, and I was an unsuspecting young, naive undergraduate at Princeton, and I went to work for him, and he assigned me as my senior thesis project, quantized general relativity. No kidding. Well, and he had a sidekick named Charles Misner, who was actually my main advisor, and well, I did learn from Misner and Wheeler that, you know, about Feynman's path integral approach, and that was great, you know. But in the end, I could only quantize the linear theory, linearize general relativity. So I wrote up my thesis about how to quantize, you know, wave equations, essentially gravitational waves, in the linear theory, and I presented it to Wheeler, and he almost flunked me. He said, "No, this is not what I want." So he gave me a B. He was being very merciful. But I learned my lesson. I switched from theory to experiment immediately. And so as a graduate student at MIT, I worked with Charles Townes, who had just invented the laser, and it was 1960, 61. And it was like a miracle, you know. It's like the Midas touch. Everything you did in the lab turned to gold. It was an amazing period of time in the 60s. And anyways, so that's my advice to budding students. You should switch from theory to experiment as soon as possible. So anyways, so such is my story. Well, I'd like to present to you a view of the Casimir effect, which I learned from Peter Maloney, and it's this idea that you should, instead of thinking about vacuum fluctuations, you should think about fluctuating currents, okay? Imagine that you have two plates, which are these black plates, and they're grounded, no charge. But even in the vacuum or at absolute zero, the fundamental mode, let's say the half sign mode here, dash red half sign, that mode will be fluctuating with an energy of 1/2 h bar omega, called 0-point fluctuations. They are going to drive currents and fields, of course. The magnetic fields are associated with these currents. They will be, both the fields and the currents will be fluctuating. But as you know from elementary physics, that if you have two currents going in the same direction, they attract each other. They attract each other. And that is the heart of the Casimir force. And that gives you the dominant contribution to the Casimir pressure. And it's actually a few lines just to calculate it. The Casimir pressure is negative, it's attractive. It's given by 1/2 mu naught is the permeability of free space, and the time average b squared of the field in inside these plates. And quantum mechanics tells us that the energy in the 0-point fluctuations is just simply the energy density times the typical volume, which is L cubed, where L is the distance, and that is in quantum mechanics given by 1/2 h bar omega. H bar omega is just omega is given by c/2L. It's just the fundamental mode, the Fabry-Perot, and you see immediately that if you solve for b squared, it goes as 1/4 power of the distance. So this immediately gives you the Casimir force, which goes as 1/4 quartic power of the separation of the plates. Okay? This is a very simple way to understand the dominant contribution to Casimir pressure. Now, I'm going to skip all this, but you can sum over all the 0-point energies of all the modes between the plates. When you do that, you get a numerical factor, which is pi squared over 240. This is just summing over all the modes, and but it's essentially the same as before. The sign is the same. It's attractive, and it's h bar c, the product of Planck's constant times the speed of light, divided by the 4th power of the distance between the plates. Again, I stress it's inverse quartic power dependence. Now, notice that the factor h bar c that determines the size of the Casimir force is independent of the of everything. It's independent, in particular, of the electron charge. You might think that this has something to do with electrons, but the electron charge does not enter into the Casimir force. Well, this suggests that maybe there is well, this is conjecture, and this is my conjecture, that in addition to the usual electromagnetic contribution, there could arise a general relativistic Casimir pressure, which is also independent of capital G, that is Newton's constant. So here's the conjecture that you can get essentially something comparable to this. Maybe the numerical factor will be different, but it's going to be on the same order of magnitude. And it will again scale as 1/4 power of the distance between this. And there's a paper which I don't have here, a guy named Quach, based on our earlier work. This is before the joint work with Nathan Enon and Thompson here. We did a paper which suggested that superconductors are mirrors for gravitational waves. And if there were mirrors, then there must be a Casimir effect. And Quach calculated that, and indeed he found it goes as 1/4 fourth power. And there was a recent experiment in Holland and Delft by a group headed by Groblacher that checked this and found that there is no such Quatsch effect, as I'll call it. Okay?
What is UG in general relativity?
Good question. It's given by some constant, I think 16 pi, times Newton's constant divided by the square of the speed of light. This is in something that is very closely related to gravito-electrodynamics, okay? It comes into the Lense-Thirring field, okay? But anyways.
What are the traces of superconductors that help that effect?
Oh, the superconductor comes in because they have the right boundary conditions, namely their mirror hard wall boundary
So
conditions.
there'll be no effects then, if there were superconductors there compared to just regular plates.
No, there's an additional effect because there are fluctuating gravitational fields in addition to the electromagnetic fields, so that there is an additional Casimir pressure, and Quatsch claimed that he calculated it, and it turns out in his calculation, which I haven't checked, that the gravitational Casimir pressure is 10 times bigger than the electromagnetic, but it's just this prefactor that's different. Okay, and that this Dutch group claimed it's not true. I mean, the experiment, which is a beautiful experiment, showed that it's not there. Yes?
Yeah, just one question. Isn't the reason why there's no electric charge in the Casimir effect due to the fact that Casimir derived this as a dipole-dipole interaction, and the dipole has a net zero charge, so that's why there's no charge. So it is nothing to do with gravity, but it's a dipole-dipole interaction.
No, this is not. You're thinking on the van der Waals force.
Right.
And the Casimir, in his calculation, did completely separate calculation from the van der Waals force, in which the only thing he assumed was perfect reflecting boundary conditions. That is that these are infinitely conducting plates. That's all he assumed. No electron charge entered into his calculation. So he got this result.
I'm just saying, yeah, there is an electric charge, but this doesn't mean that it must be gravity. That's all I'm saying.
Oh, no. It could be any field that has fluctuations in it. Okay? So the conjecture here is that in addition to electromagnetic fields, which we know are fluctuating due to Lamb shift and everything else, we know, well, the conjecture is that there must be zero-point fluctuations in the gravitational field. That's what my thesis with John Wheeler was all about. And if that is true, there should be a gravitational analog of the Casimir force. Okay? That's all I'm saying.
But that might not, in a gravity well, though, your gravity of the gravity well takes precedence over anything that's fluctuating. So a test of what you're saying on Earth probably won't work. You'd have to go out away from all large masses to do this experiment.
No, I don't think that's right, because you see, as long as the boundary conditions are satisfied, that is to say that you have found a substance, and this is a big if that superconductors are real mirrors for gravitational waves. That statement is true whether you're close to the Earth or far away from the Earth. And once that boundary conditions, that is perfect reflection, is imposed on the gravitational field, you're going to get the Casimir force out, even on the Earth.
Well, I still would think the gravity the gravity of the Earth would swamp any other fluctuations of gravity of the Earth.
Well, that's a key point, and this goes back to our. You should in my paper for Heidi's previous conference in the aerospace proceedings, which was published in a strange journal called Journal of British Interplanetary Society. Well, in that paper, I pointed out that actually gravitational fields are of three kinds. There's a scalar, and there's a vector, and there's a tensor field. And they correspond to, this is a very brief aside, to sources, the stress energy tensor T00, that's Newtonian gravity, feels like the Earth, T0I, which correspond to Lenz tearing fields, for example, the rotating Earth, frame dragging. And then finally there is Tij, space-space components, and they are the source of gravitational waves. Now, we know from electromagnetism that when you consider the dielectrics and matter responds linearly to fields, like applying electric fields between in a capacitor, you get a dielectric response. The dielectric constant is not at all related to the diamagnetic response, say if you apply a magnetic field to the same material. The dielectric constant has nothing to do with the diamagnetic constant, because the nature of the electric field is completely different from the magnetic field. You cannot just say, but in gravity you have a third kind of field, and besides the gravito-electric and the gravito-magnetic, there is a third kind which called the gravitational wave fields, Hij fields, which have yet a third kind of response, which we gave a name in this paper. We call it permeativity, just to invent a new name in analog with what we know for electromagnetism, which is permittivity in response to electric fields, permeability, which is response to magnetic fields. There is in gravity a third kind, which is permeativity. And we don't have any idea what it is until you measure it. Okay? The conjecture here is that the permeativity for superconductors is very large. It's because it's a mirror, basically, for gravitational waves.
You have resonance and you might have amplification.
Yes, exactly. And
Why end up with different wavelengths that fit in there compared to if there's no superconductor?
exactly. You have exactly the same problem as
Entirely different problem.
but it's an entirely different problem. And furthermore, this is to summarize the results for the previous paper for the aerospace JBIS contribution.
But I would almost expect that the gravitational portion of these permittivities
Permeativities. So say it after me, please. Permeativity. Okay? New word.
would just be a combination of those, the dielectrics and the magnetics, which I think were the
No, because the fundamental nature of the field is different, so you have no idea of how big it's going to be. You have to measure it. You cannot just extrapolate, say, oh, I know the permittivity, I know the permeativity, therefore I know the permeativity. No, it's impossible. You have to go to the lab and measure it.
Okay, are you going to describe the experiment later?
Yes.
Then let's go.
Yeah, okay. Okay, but just one final comment. This is really important, but I don't think I'll introduce this in this present conference, but I did introduce the idea in the previous aerospace. You were there?
Yeah.
Okay, well, but some of you weren't there, so let me just, if you have mirrors for gravitational waves, then you can make a laser for gravitational waves.
Yeah.
And that's really important, because then we can make lasers for
But
gravitation.
you're going to have the amplification going this way. How do you get it going this way?
Let me just state it in words. If you have two mirrors, you would think you have to have an inverted two-level system in order to get an amplifier going, okay, like in the laser. You have two mirrors, inverted two-level medium, and away you go, above threshold, it lasers, okay? Well, in this paper that was in aerospace previous conference, the idea is very simple. If the mirrors move, then you don't even need a two-level medium, because a moving mirror is like a moving piston, and a moving piston can do work, and the work that it can do can amplify in a process called parametric amplification. Okay, it's like a child on a swing. When you push a child on a swing, you can amplify the motion. Well, you can do that with a moving mirror, and above a certain threshold, which was calculated, but we need to. Jonathan has been looking at this problem. What is the threshold for this kind of laser? But in principle, you don't need a medium at all. You just need a moving mirror, a moving boundary condition, and that's.
Physically, you're so thin now. You tell me you're going to vibrate from there? Wow, that's a tough job physically.
No. I'll show you that you can do it with microwave frequency cavities. You don't have to have it really close. You can have it spaced by half a microwave wavelength, and you can make moving membranes move at microwave frequencies. Hold off, and I'll show you how. Okay, so. The bottom line, though, is so important, I want to emphasize it. I think that we can, in the future, make lasers for gravitational waves. And this will completely revolutionize communications. For example, DARPA should fund me for this because, for the following defense reasons. We can get rid of all the satellites and communicate directly through the Earth using gravitational waves instead of using satellites.
For imagery
and so on and so forth. I mean, completely a new world will open up if what I say is true. You should fund me, Mike Fitting.
He's a tough guy, man.
To have a mirror for gravitational waves, you need to have a speed of sound equal to the speed of light.
Yes, I'll come to this point. Yes. Yes. Yes, that is the key question, and I'll come to it, okay?
Okay.
I'm so grateful to you, Jose. You always ask the right questions. Yes, question. Did you have a question? Oh, okay. Any other questions so far? Okay, so good. Oh, I am wrong. How do I get it? The upper one?
A lower one. Point it at the computer.
Oh, I see. Okay. Okay, now this is new stuff. Supposing that we consider the following problem. We have the Casimir effect again with our two plates grounded to get rid of the charge, but we coat them with superfluid helium. So these blue rectangles represent superfluid helium coats. And how would you do this in practice? Well, it's very easy in our dilution refrigerators, which, I don't know, do you have a picture of our dilution refrigerators? Oh, it doesn't matter, okay. Well, you can cool these plates. They could be superconductors, they could be normal metal, down to, in our case, around 30 millikelvin. That's about sort of base temperature. And it's so cold that if you emit some helium atoms, helium-4 isotope, they will condense or absorb onto these cold surfaces. And they will form a superfluid helium coat like this, okay? And you can make many monolayers so that it builds up, such that this distance A is a small fraction of the original distance, let's call it D, between the plates. In other words, there's a thickness B, and D is A plus 2B, okay? So this is the kind of geometry I'm going to consider. And now we can raise a really interesting question. What is the Casimir pressure between the plates for such a geometry? Now, Lifshitz solved the problem of the Casimir force between two dielectrics, two dielectric slabs without the metallic substrates. And he got the following, I'll call them Lifshitz factors, which corrects the original Casimir pressure formula. Here it is, h bar c over L to the fourth pi squared over 240. And the Lifshitz factors are kappa, the dielectric constant, minus 1 over kappa plus 1, quantity squared, times a Lifshitz function, which is a slowly varying function of the dielectric constant on the order of unity, okay? So the question that I raised is this: is the Casimir force in this kind of geometry determined by an effective length scale, which is A, the small gap, or is it D, which is what you might expect naively on the basis of the fact that the dielectric constant for superfluid helium is 1.057. It's very, very close to vacuum, okay? So there's almost no change. So what we need to do is measure this in an experiment, and that's what we are planning to do, okay? And this will address certain questions about superfluid helium physics that actually, let me go back one question. This experiment was stimulated by a question from George Chapline, which says, can you do an experiment on Casimir effect in superfluid helium? Because George Chapline and also his well-known collaborator, Bob Laughlin, Nobel Prize winner for his work on Laughlin wave functions, believe that the vacuum is actually like superfluid helium. And in particular, the vacuum, when you approach the event horizon of a black hole, undergoes a quantum phase transition at the event horizon. And so he said, simulate this by looking at superfluid helium. So this was in response to George Chapline's question. Okay, any questions about Lifshitz? Okay, no, all right. Next question. Here's something that I will write up for this conference. I believe that we can do a very simple modification of the previous geometry in which the black stuff, the plates, is a type 2 superconductor, for example, niobium, which we work with a lot in our lab. And you can apply a magnetic field to the niobium as it goes through its superconducting transition, and it will trap Abrikosov vortices in a lattice, hexagonal lattice array. Okay, let's call that the Abrikosov vortex lattice, and that is indicated by these yellow lines. They're the cores of the Abrikosov vortex lattice seen in projection. Okay. Now let's repeat our idea of cooling this down to 30 millikelvin and absorbing helium atoms onto this cold surface. Well, here's an important fact that you should know. Helium atoms are diamagnetic, okay? But they are going to avoid these cores of the Abrikosov vortex because the magnetic fields there are enormous. They're on the order of Tesla. So the helium atoms will not absorb at the cores of the Abrikosov vortex lattice. My conjecture, and this has to be checked, is that this will induce vortices, which I'll call Feynman-Onsager or vortex lattice in the superfluid that will be absorbed to the niobium superconductors. And this is another, I know this is speculation upon speculation, but forgive me for, there is something called Young's principle that you may not be familiar with. Yes?
Just out of curiosity, what's the distance, what's the magnitude of the distances between the plates?
Oh, it's on the order of nanometers.
Nanometers?
Yes.
Okay. So what happens if you actually get the superfluid helium across the center?
If it fills in the gap, then of course there is no gap, okay?
Right.
And then it just becomes, well,
solid device.
Yeah, it wouldn't be interesting because, yeah.
How you maintain that gap is going to be a really interesting.
Oh, yeah, that's right. And how you monitor this is an important experimental question. How do you measure the gap? Okay.
Yeah,
So it's uniform from the top to the bottom instead of fluctuating around as you go.
Oh, okay. Well, there's an answer to that, which is that instead of using parallel plates, you use Lamoureux's trick, which is you replace one of these flat plates with a spherical plate. Okay? And that's how Lamoureux did his Casimir experiments, and that's what you would do in practice. And also there's another technical feature that must be mentioned here. The atomic force microscope is the way to make these measurements, okay? So some technical details I'll skip, okay? Does that answer your question, Greg?
Yeah.
Okay. So let me introduce you to something that probably you don't know about. It's called Yang's principle. Yang, in 1961, with Nina Byers at Stanford University, wrote an important paper which explained why flux is quantized in type 2 superconductors in units of Planck's constant divided by twice the electron charge. Okay, but he introduced a very important principle, which now I'll call Yang's principle, which is that the wave function is single-valued in multiply connected geometries. Imagine you have a superconductor with this in the form of a donut with a hole in it. As you go once around it, you come back to the same point with the same phase. That's Yang's principle. Okay, well, and that I'll just state the final result. This leads to the answer to Jose's question. The speed of sound, if you like, becomes infinite, because the Yang's principle basically says that the phase of the wave function cannot change in response to the incident gravitational wave. So it behaves like a hard wall boundary condition. This I'm skipping details. This will be in the paper that I present for this conference.
And you're comfortable with the idea of something that's not only superluminal, but it has this infinite.
It's infinite permeativity, to give you in other words, if you were to measure the linear response to gravitational waves, okay, you will find the permeativity is essentially infinite, okay?
Now you're an expert, you consider yourself an experimental physicist. Is there any experiment?
Some people call me a quasi-experimental physicist.
Is there any experimental, well, not experimental, or observational basis of any material having a speed of sound equal to the speed of light, or not just
yeah, there is, but from astrophysics, the equation of state of neutron stars has a speed of sound which exceeds the speed of light. This was pointed out by a guy, his name at Columbia, begins with the letter R, I forgot. But anyways, the equation of state for neutron matter is so stiff that, and in fact this was a paradox in those days, the speed of sound he got was greater than the speed of light. Okay? Yes.
So the gravitational permeability you're saying is infinite in a superconductor?
Well, I don't. Nothing's ever infinite, but for all practical purposes, it's so large that the important thing is that. That in Lipschitz's formula for the Casimir force, kappa is so large that for all practical purposes, the first Lipschitz factor, which is kappa minus 1 over kappa plus 1 quantity squared, is unity.
Because if a superconductor would have an extremely large gravitational permeability, then if you would rotate it, you would create a huge ferromagnetic field.
No, I think what will happen is it will quantize the gravitational flux in quanta of h over something. I don't know what it is, but if you try to do that, it will refuse to depart from a quantum of flux of whatever the gravitational analog of h over 2e is. I don't know what it is, but it's going to refuse to budge from that value. That's my prediction. Now, to answer your question in a little more detail, the permeativity, as I call it, is so large, but it's not infinite because there will be some kind of length scale. Let's call it the gravitational London penetration depth, which has to be measured. We don't know what it is. But that it has to be factored into this problem. And we don't have any idea how big it is or how small it is at this point, because we don't have any experiments to guide us. Okay.
You measured the London penetration depth for gravity-magnetic fields?
Yes.
Okay.
And that has never been done.
Because you cannot measure gravity-magnetic fields in the lab?
Yeah, exactly. But, oh, I hasten to add that you are thinking of the gravitomagnetic field that is the analog of, well, this is the Lense-Thirring field. But what is important here is not that field, but this third type of field, which I don't have a name for, which is HIJ, ta-ta, as we call in our paper. It's the tensor, not the vector, gravito field that is responsible for the kappa here. This is not what you worked with. What is the guy's name that you worked with on gravito electromagnetism? What?
Clovis de Matos.
Oh, de Matos, that's it. No, this is a different kind of field. Okay. Okay, now I come to the subject which is of great interest to this audience. Casimir effects may allow for wormhole interstellar travel, and you might think, fortunately, I can cite a reference because I think this is really crazy stuff, but it's been published in the open literature and by a very well-known guy whom I greatly respect. His name is Kip Thorne at Caltech. Kip Thorne wrote a paper in 1988 called Wormholes, Time Machines, and the Weak Energy Condition, okay? I think it's worthwhile for me just to read the abstract just to show you how wild this paper is. Jim, are you awake?
Yes.
Okay. Listen to this. I mean, even to this day, it amazes me that Kip Thorne was bold enough to publish this paper. Here it goes. It is argued that if the laws of physics permit an advanced civilization to create and maintain a wormhole in space for interstellar travel, then that wormhole can be converted into a time machine with which causality might be violatable. I think he invented a new English word. Whether wormholes can be created and maintained entails deep, ill-understood issues about cosmic censorship, quantum gravity, and quantum field theory, including the question of whether quantum field theory enforces an average version of the weak energy condition. Now, a much more readable paper, and I just finished reading this. It's really wonderfully written paper. It's very pedagogical. Even a graduate student can understand it, right? Jonathan, you can understand this paper. Merced and Thorne, wormholes in space and their use for interstellar travel. Interstellar travel. A tool for teaching general relativity. And this is a marvelously pedagogical paper published in the American Journal of Physics. I highly recommend it. Okay. So Now, I'd like to introduce you to the weak energy condition, okay? This is my understanding of it, and maybe not completely rigorous, but here is what the physical meaning is. The weak energy condition states that although the pressure due to matter can become negative, okay, negative pressures can exist. Therefore, pressure can contribute as a negative source to gravitational fields. It could never become so negative that it overcomes the contribution of the positive rest mass density of the matter, so that there results a net anti-gravity, that is a repulsive kind of gravity, okay? So if you know anything about general relativity, we say, take a look at T00, the time component of the stress energy tensor. You can put pressure and energy density in as separate sources of Newtonian gravity even, okay? And the pressure can never overcome the contribution of the rest mass energy, okay? That's the weak energy condition. But Thorne says sometimes this might be wrong, and he even states that it's the Casimir effect, which can show this is wrong, okay? This was introduced by Ellis and Hawking in their book, but it may be wrong, because quantum mechanics trumps, no pun intended, trumps gravitational general relativity. So Thorne calls any matter that violates this weak energy condition exotic matter, and we are now talking about Casimir matter in particular. And so the question is, can the Casimir effect lead to such exotic matter? And I cite this pedagogical paper. Yes?
Okay, now I'm really lost, because quantum mechanics has a universal time.
Yes.
And general relativity has
local time.
Local time.
Yes.
And that's number one. And number two, now we're talking about wormholes that can be used to make a time machine.
Yes.
You could, I guess, fabricate a wormhole to have a closed time loop.
Yes, right.
That seems like a breakdown of general relativity.
Yes, this is precisely the point that George Chapline made to me, okay? He believes that this is a signal of the breakdown of general relativity, okay? Who knows if George is right or wrong until we test it, okay? This is my point, okay? And I think we can test it in the lab via the Casimir effect. That's the main burden of my talk here, okay? So can I proceed?
Yeah.
Okay. How much time do I have?
As much as you want.
About 10 minutes.
Oh, okay, all right. I'll try to speed up. Okay, so here's the possible design of a wormhole for interstellar space. This is taken from Thorne's paper in Physical Review Letters, or my reading of it. Basically, you construct two conducting shells, both made out of, well, let's say superconductors to be concrete, and you charge the inner shell through a battery to ground, such that there's a charge that generates an electric field that radially goes out, but of course inside it's just a Faraday cage. But, this is a big but, between the two shells there is a Casimir vacuum that's indicated in yellow, so that you have negative energy density in that region. Suppose that negative energy density is so large that it violates the weak energy condition. Then he says you can create a wormhole. Okay, that's the bottom line of his theory. So if you drill a hole, say an entrance here, and you pass a spaceship in through this entrance, and you went through this wormhole, you would end up in a different universe. Okay, that's Thorne's paper in a nutshell. Okay, now, yes?
What's the scale of those shells?
That's an excellent question. The answer is that it has to be extremely small in order for the weak energy condition. In practice, the rest mass energy of the shells would overwhelm the negative energy unless the shell was extremely thin. Okay, I couldn't give you an actual number, but it's
If you want to pass a spacecraft through a hole.
Oh, well, Thor says, well, he puts it this way, that the energy density has to amount to about a Jupiter-sized mass.
Yeah.
Okay, Jonathan.
So I'm kind of thinking about the energy density of the two cylindrical shell. The shell will have some gravitational field associated with it, which in and of itself will also have some positive energy, not negative energy, which might shield out the effect of the negative energy.
Well, that's the weak energy condition. That the assumption is that positive energy is canceled out by the negative energy contribution of the Casimir.
But I guess what I'm saying is you have to do the numerical calculation.
Oh, sure.
It is.
Yeah, well, that's what Thorne did, okay?
If I go through a Hollywood wormhole, the comment is that everything that's inside got air, nice temperature and everything like that. If you look at these models, will I see exposure to space weather?
What do you mean by space
Gamma
weather?
rays, particles from the sun?
I don't see why this would shield you against that. Yes.
Yeah, there's a whole literature that follow this paper that you mentioned, which is there's a distinction called transversible and non-transversible.
Oh, thank you, John. Yes, yes.
Other ways of building wormholes that don't involve Casimir plates.
Yes, in fact, Jim Woodward's method is one of them, and I'll get to that. Okay, that's a very important point. There's something called traversable wormholes, and I forgot to mention that. Okay, and I'll come to Jim Woodward's book, which I've been reading over and over again, called Starships and Stargates. I think that he's onto something. Well, yes, great.
So let's say you had one of these things and it worked. How do you know that whatever you send in there went through? How
Oh,
would you know?
You can go through yourself and find out.
Pull it back out?
well,
Pull it back out? How do you know it went through? I mean, if it-
well, to say, let's put it, supposing you had an observer nearby inside the shells, and you,
You know it's a wormhole, not a black hole.
no, it's just need not be small. These shells may be large, but it's the gap between them that's very small, okay? Okay?
But would something have to come back through?
No, it could. It's in a transversible wormhole. You could come back through. Okay, but to the spaceship coming through the entrance would look like if it went through the wormhole, it would disappear and appear in the other universe.
Yeah, I don't think that's what Thorne said. He was talking about wormholes that had been local mouths and you put one.
Oh, right. But
The other universe business, I don't know if that's somebody else.
no.
I don't think if Thorne ever talked about wormholes to other universes.
Well, in his other paper, the American Journal of Physics paper, my reading of it is that it connects to a different universe, but maybe I'm right or wrong.
Pulling the wormhole out of the quantum vacuum, and I guess it depends on what kind of wormhole you pull out of the quantum vacuum before you stabilize.
Yeah, exactly. Yeah, that's in order to answer the question, can I build a time machine? But in his American Journal of Physics paper, it's just, what kind of universe would we live in if you had a wormhole? And if you look at just a picture in the figure 1, it's a wormhole that connects two universes, basically. Okay, or even yes?
When you say Casimir vacuum, does that mean there can be no matter within that?
Yes, it's a vacuum, yes. Yeah.
Where are my exits? How do I get out of here?
What do you mean?
I come in somewhere, where do I know where I'm going to go?
Yeah. According to, okay, let me, yeah. That is, well, if we believe this in classical GR, then it's general relativity, it's determined by solutions to Thorne's metric, which is this, okay? The metric here is written down here, and it's different from the usual Schwarzschild metric in that the, the G00 component, that is the time component of the metric, is an analytic function, not a singular function like in the Schwarzschild solution. It's exponential minus 2 phi, where phi is a kind of gravitational potential. And physically, it's the gravitational redshift function. That's his name for it. Okay, it tells you how much gravitational redshift you see as a distant observer looking into the wormhole. Okay, and then there is another. This is a G sub r, or the radial component of the metric, which is describing the shape of the mouth of the wormhole, or the throat. He calls it a throat, I call it a mouth. But okay, this is also of the same, this is the Schwarzschild kind of function, except he allows B to be an arbitrary function of R. Okay, that's the trick. Okay?
But you have a singularity when B is equal to R.
Yes, but that depends on the function of R that you choose, so, okay? And you can choose it such that it's doesn't have any singularities, okay? And so there are no event horizons in this
So
metric.
I can't think of a wormhole as a singularity.
No, that's important. He stresses this. There are no event horizons in this metric, okay? So therefore no problems, at least at this level, with Chaplin and Laughlin's paper, okay? No singularities, no Schwarzschild-like singularities. You want to comment on this, Jonathan? Okay. All right, I better speed up. Sorry to take this be so slow. So I'd like to just go through the rest of my slides very quickly and answer certain questions. Can negative energy densities in the Casimir effect stabilize the mouths of such wormholes? And I first want to cite that dark energy, for which Saul Perlmutter won the Nobel Prize in 2012, here's his Nobel lecture, is a kind of anti-gravity, okay? But I want to show you that there is even already present in the lab and a phenomenon which we can interpret as anti-gravity in quotation marks. Here it is. I call this the creepy superfluid film. And this is a real phenomenon that was discovered by Allen back in the 30s, I think, or 40s. And here it is. Consider a superfluid helium bath. And here's the wall of the bath, here's the bottom, and so on. Okay, now what is observed is that the superfluid helium bath creates for itself a film, and this film creeps up the walls and goes over the top, and then it creeps down the outside wall, and they observe this. Drops of superfluid helium drop off the exterior wall in a kind of super leak. I call it a super leak because this is as if the superfluid helium tunneled through the wall. It's not real tunneling, it's quasi-tunneling. But nevertheless, this is really a phenomenon that has been observed. It's called superfluid helium creep. And this is I want to commit to you a negative Casimir effect. okay? Already, this phenomenon.
Why is that the negative Casimir effect as opposed to a fluid effect?
Oh, you can also think of, in fact, I'll come to it as a fluid effect, okay? But it's a quantum fluid effect.
Yeah.
Okay. Yes, Greg.
Yeah, so if you have this kind of phenomenon, how is it you propose to coat your plates with superfluid helium?
Oh, yeah, that's an excellent question. Well, it depends on how you prepare the, in this experiment you have a bath. In our apparatus we don't start with bath, we start off with cold plates and you absorb helium gas onto the cold plates.
Cryo-pump the helium.
Yeah, exactly.
Okay. And it applies in
Yeah. Yeah, so that's a different situation. But I want to stress that this can be interpreted as a Casimir effect. Here it goes. Start with the uncertainty principle. And the uncertainty principle tells you that if you confine an atom to a distance delta x, you necessarily create a uncertainty in the momentum of the confined particle, say helium atom, confined to the thickness of L, which I'll call L, the film thickness. And therefore you can solve for delta P, and that's the m delta V, that's the uncertainty in the velocity of the atom, and it's given by h bar over L, the thickness of the film. Okay, m is the mass of the helium atom, and delta V is the fluctuating, quantum fluctuating film velocity. Simple undergraduate quantum mechanics. Okay, now comes to my answer to Jose's question. You can imagine this as a fluid mechanics problem and think of this as a Bernoulli pressure, okay? So if you calculate the kinetic energy per atom, it's 1/2 mv squared, delta V squared, and it fluctuates, so I had to put a bar there. And that can be rewritten as delta P squared over 2m. I should have put a bar here, sorry, I forgot that, which is given by order magnitude wise, Planck's constant squared divided by 2ml squared, okay? Now, that's the kinetic energy per atom. Now, summing up for all the atoms, we get Bernoulli's pressure, which is rho, the mass density, times delta V squared, and that is 1/2 rho h bar squared over m squared L squared. Let's call this the Bernoulli pressure, okay? The Bernoulli pressure is the source of the creepy superfluid because it's a negative pressure. It's a suction, and it sucks up self-suction, if you like.
Store negative energy.
What?
How would you store negative energy?
You don't need to store it. It just naturally happens when you have this creepy film.
Okay.
Okay, so now comes the heart of the physics, which is dynamics. You set the Bernoulli pressure equals the hydrostatic pressure. So here's Bernoulli, 1/2 rho V squared, and you set that equal to the hydrostatic pressure, rho G, this gravitational constant of Earth, times h, the height of the film, and you can solve for L as a function of h, and lo and behold, it's very slow dependence, 1 over square root of h. It's a very slow function, and you can get the constants involve h bar, so this is a quantum effect, okay? And so we should ask the question then, how high can this superfluid go this creepy film? Well, it's very simple. You can solve, instead of L in function of h, you can solve for h in function of L, and I think I'll skip all the algebra. The final result is 40 meters. You can go up about 300 feet high. It's a high building. It's a wow. It's another amazing. Okay. Well, of course, this experiment has never been done in the lab because it's hard to do. But another question you can ask is, how fast is it creeping at the very top? And the answer is, it's given again by the uncertainty principle. It works out to be about 30 meters per second. It's pretty fast. And the typical energy at the top is the roton. I won't go into this, but it's around 160 micro.
16 microvolts.
Yeah, 16 microvolts. Thank you.
It sounds to me like you can create a home community electrical device out of this thing, right? You can go up the wall, gravity pulls it down to a needle, the needle turns and brings it.
Yeah, but then you run out of helium. Remember that, let me just...
Well, you got the helium, you're creating electricity.
Oh yeah. Yes, you are absolutely right. You can let these drops fall onto a rotating, what do you call that? Turbine. Okay, turbine, and generate electricity. But of course, this is a finite bath, and it will eventually be emptied out, so it stops. Okay. So this is. But I want to just stress the physics. The physics here, as Jose mentioned, is that it's Bernoulli pressure, it's fluid dynamics, nothing more than that, but it's quantum, because it's quantum pressure which is generating the Bernoulli pressure. And this quantum pressure is, I'll call it a Casimir-like pressure, because this is not due to the fluctuation of electromagnetic fields, it's due to fluctuations in the superfluid velocity field. Okay, so that's the answer to your question. Okay, now I'll be very quick for I'm running out of time. How high in principle can a superfluid creep? Okay, and my answer to that is there is no limit, because the uncertainty principle is what determines how high the barrier it can be, and there is no limit. The uncertainty principle is independent of gravity. Okay, so there exists, therefore, in principle, no horizon limit to superfluid creep. Even in a black hole, it could creep out of the black hole, believe it or not. So, for example, a photon superfluid, and I wrote a paper on that, here's a reference, can in principle achieve an escape velocity which exceeds the speed of light. Therefore, you can escape out of a black hole.
Okay, I read where they treat the vacuum. Does that mean that the expansive universe then is just a superfluid creep of the vacuum?
Sorry, can you repeat your question?
I've read where they have an analysis to the vacuum as being a superfluid medium.
Yes.
So if you take that analogy,
yeah,
the expansion of the universe is a superfluid creep.
I never thought of it that way, but it is closely related with George Chaplin's question to me, because he has this model of the universe vacuum as superfluid helium. So it is related to superfluid creep. Okay, so time is really running out. I better skip over this very quickly. I wrote a paper where I suggested that photon gas can become a superfluid if the photons can interact with each other. It obeys something called a Vogel-Lyubov dispersion relation, and you can show that this leads to an escape velocity on the order of the speed of light. Therefore, it can escape through the event horizon, in principle, okay? So I'll ask this as a question and let you think about it. Can this upwards superfluid creep effect be viewed as a kind of anti-gravity effect? Okay, it's up to you to answer this question, okay? Well, now I think I'll skip over this very quickly. This is another warp drive introduced by Alcubierre back in 1994. He wrote a paper which is based on standard general relativity. He wrote down a metric in which he showed that you can have flat space-time in the middle of a spacecraft. In the middle here. And in front of the spacecraft, space contracts in the front of the spaceship due to the Casimir effect. But in the back, it expands again due to the Casimir effect. I should mention that the Casimir effect can have both signs. It can be positive and it can be negative, depending on the topology of your Casimir vacuum. Okay, well, he showed that then if you write down the metric, and it's a very simple metric, it's here you complete the squares in this fashion, and it has an obvious physical interpretation that to a distant observer, the velocity of the flat part of the spaceship, that is the platform, as I call it, is v sub s, that's the velocity of the spaceship, is a platform function which is explicitly this combination of hyperbolic tangent functions. You parameterize it by two parameters, sigma and r, and it tells you how big that platform is. And lo and behold, of course, the spaceship is traveling with a velocity v sub s. Here's the Cartesian form for the distance, the position of the middle of the platform. You plug it into Einstein's field equations, and you find, of course, the stress energy tensor is negative. So he himself points out all the energy conditions, not just the weak one, but the strong and the dominant, and then all of them are violated by his stress energy tensor. Okay, all of that goes out the window, but he says, oh, but that's quantum mechanics for you, or Casimir vacuum violates all of the energy conditions. And he says this is indeed possible because we know the Casimir effect exists. Okay. Well, this implies, and he shows that there is a faster than light effective global velocity of the spaceship is a result of his calculation. So warp drives exist. That's what he concluded. However, there are no violations of causality here, including no closed time-like curves. Unlike Thorne, he has no closed time-like curves, so no violations of causality can result from Alcubierre's solution. Now I turn to Woodward's work. The Woodward drive, however, can give rise to wormholes. However, this Woodward drive is classical and not quantum, okay? Nevertheless, a Woodward-type wormhole drive, I think, becomes possible, and I think we can build it in a prototype of it in our laboratory, and I'd like to show you how very quickly, and leave this to Jonathan to fill in the details. This is your, I know if you're finished with your PhD thesis almost, and this is beyond your thesis. So let me give a very simple Gedanken experiment of a Woodward drive. You're supposed to have two LC circuits, and the two inductors L are coupled by mutual inductance, where the magnetic field threads through both inductors, okay? This allows a coupling between the energy in the upper LC circuit to the lower one, such that there is a sloshing of the energy from the upper to the lower, back to the upper, such that the center of mass goes between the upper and the lower, back and forth, because E equals mc squared means that the rest mass energy goes up when the energy is in the upper LC circuit, and then it goes down to the lower when the energy has sloshed completely lower. It ends up, the center of mass is here. And now comes the magic. If you insert a PZT, piezoelectric transducer actuator, in the middle to time it so that it coincides with the sloshing, you get a thrust. Okay? Am I right, Jim? I hope I haven't. Okay, so now here is the formula for Woodward's Mach effect, and there are two terms. He calls them Mach effect number 1 and Mach effect number 2. Notice there's this minus sign for the second one, and this is a sign of the wormhole. Okay. So in principle, we can make a wormhole using this Mach effect. Okay. And here's how well, I think I'll skip over this and just get to the point. Okay. Yes.
Can you go back to that equation, please? So, that can be expressed exactly as the log derivative.
Yes, of course.
Like that.
Yes.
But anyway, just looking at that equation, for the second term to exist, for the whole thing to be negative, you need to have the derivative with respect to time of the mass density to be practically constant, so that the second derivative disappears or is negligible compared to the first derivative.
Oh. And so what is your point? That
Then it doesn't seem feasible.
Oh. Well, I would put it differently. I would say that the second term can dominate over the first term because it's nonlinear, okay? And if, in principle, this is hard to do, you can make rho naught or its derivative very, very large. It dominates over the first term.
But if you do this with a sinusoid, for example, it won't work.
No, well, I didn't say I would use a sinusoid for this, okay? But I'm making the assertion that there are circumstances in which the second term can dominate over the first one, in principle, okay? Are you happy?
They have to be examined as far as...
Okay, agreed, okay. All right. All right. So here's a way to do it, okay? And this is completely hypothetical, and maybe Michael, you can fund me for this. So here's the microwave analog of the two LC circuits. You have two microwave cavities, and these can be superconducting radio frequency cavities of the sort that we have built in our lab, with Qs on the order of 10 to the 9 and higher, okay? Qs of 1 billion or higher have been achieved with superconducting niobium cavities, and we've made some of them, okay? Not the highest ones. And these can be driven by I call a membrane actuator, which replaces the PZT actuator in the following way. And I should give credit to the graduate student who invented this device. It's a conical tip driver, okay, where you take a coax and you sharpen the central conductor into a point. So it's a conical tip, and the electric field there drives a membrane back and forth, and it can have any non-sinusoidal waveform that you like, because this is a coax, okay? So this is a microwave cavity Woodward drive, and you can drive the center of mass back and forth because the energy sloshes between the upper and lower microwave cavities. And you can make a Woodward microwave drive. Now, the key point is this, and this answers your question about how it scales. So let's scale Woodward's formula based on a very conservative assumption, which is that the scaling goes as the frequency squared, and this is based on his formula, where the time derivative can be replaced by a frequency, and you can see immediately it scales as the square of the frequency. So let's go from Woodward's measurements, which are that you have a thrust of the order of 1 micronewton at 40 kilohertz, roughly. And let's scale up in frequency to 10 gigahertz where we're working in our lab, okay? And calculate what the thrust is based on the 1 micronewton number. And the answer is 6 metric tons. 6 metric tons. You see this is important. Yeah, this is, you should fund me for this. Hint, hint. Okay, but of course, I should hasten to add that in Jim Woodward's book, he states that the scaling goes as the sixth power of the frequency for reasons that I won't go into, but I think that let's be conservative and let's assume it only goes up as the square of the frequency. That's good enough. This is really, really interesting and important. Okay, please fund me. Okay, that's the end of my story. I would like to summarize my talk. The first point is that experimental tests of quantum gravity, experiments in quantum gravity, can be done, especially where general relativity and quantum mechanics are in conflict, and it should be possible using Casimir or Casimir-like effects. Okay? Second point is negative energy densities are equivalent to negative pressures which lead to, for example, the upwards creep of superfluid films, and which has been seen. And if these negative pressures violate, of course they do violate the negative energy condition, that is exceed the negative, the negative exceeds the positive rest mass densities, then negative or repulsive, or may I use the word anti-gravity, results. This may lead to traversable wormholes and Alcubierre drives. My next penultimate conclusion is Woodward drives should be scaled up to microwave frequencies. Wormhole drives using the Woodward effect should be re-looked at. Okay, thank you very much for your attention.